So last time we defined compact sets, and if we look at the definition, the fact that every open covering should have a finite subcover is a hard condition to check, right? You don't want to go through every open cover and check if you can always find a finite subcover, and it would be really nice if there's an easier way to classify these sets so that you can use their nicer properties. And that is called the Hein-Borel theorem, which works for metric spaces, and we'll proceed towards that. Theorem 2.38. If In is a sequence of intervals in R, is a sequence of intervals in R of, let me say, closed intervals in R, closed intervals in R1 such that Ik contains Ik plus 1 for every k is equal to 1, 2, and so on, then the intersection of all of these, then intersection I is equal to 1 to infinity, k is equal to 1 to infinity, k is non-empty, is non-empty. Okay. We just saw that this is true for compact sets, right? We want to prove this for closed intervals. As of now, we don't know if closed intervals are compact sets or not. Eventually, we want to show that, but here's the proof. If I is equal to AB, IN is equal to AN, BN, let E be the set of all ANs. Let E be the set of all ANs. Be the set of all ANs. Okay. Well, then E is bounded above, then E is non-empty, and bounded above by any Bn, say B1, by B1. Okay. Therefore, it has a supremum that X is equal to supremum of E. Okay. If M and N are positive integers, if M comma N greater than belong to N, and sure, and M smaller than or equal to N, then we have that AM smaller than or equal to AN is smaller than or equal to Bn is smaller than or equal to Bm. Right? Therefore, well, since X is the supremum, we get that AM smaller than or equal to AN smaller than or equal to X smaller than or equal to Bn smaller than or equal to Bm for every N and M, for every N comma M. Right? And therefore X belongs to every single therefore X belongs to In for every N belonging to for every N belonging to N. Therefore, X belongs to intersection In. 1 to infinity. N is equal to 1 to infinity. Okay. So we have shown that even the without needing the proof that a closed interval is compact, we can still show that their intersection is non-empty. Okay. Now, this is true for an interval in R1. Let us try to show for an interval analog of an interval in Rn. So, theorem 2.39. Theorem 2.39. Let k be a positive integer. Let k be a positive integer. If In is a sequence of k cells, k cells, such that In contains In plus 1 for every n 1, 2, 3, 4. N is equal to 1, 2, 3, dot, dot, dot. Then their intersection is not empty. Then intersection n is equal to 1 to infinity In is non-empty. Okay, so first of all, in case I don't remember if I defined note, I don't remember if I defined a k cell or not. Probably skipped it because we didn't need to define it. But a k cell is basically not a k cell in Rn of, did we define it only very specifically for just give me half a second. I think it's defined only for Rk. Okay. So a k cell in Rk is the set of all points, is the set of all points x belonging to Rk. X is equal to x1 dot 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 xk belonging to Rk, such that whose coordinates satisfy some inequality, whose coordinates satisfy some inequality, satisfy the inequalities. So inequalities ai smaller than or equal to xi smaller than or equal to bi for every I for 1 smaller than or equal to I smaller than or equal to k for some fixed or given for some given a is equal to a1 to ak and b is equal to b1 to bk. Okay, so for example, in particular, a 1 cell is an interval, as we saw previously, and a 2 cell is actually a rectangle. Okay, 3 cell is a cuboid, and 4 cell, well, is generally called a 4 cuboid or stuff. Okay, so proof. oops. Let in consist of all points. Consist of all points. X is equal to x1 to xk such that ax comma j is smaller than or equal to xj, smaller than or equal to bx b. So it should have been an n comma j. An comma j is smaller than or equal to xj, smaller than bn comma j. For every one smaller than or equal to j, smaller than or equal to n, and I'm sorry, k, and n is equal to 1, 2, dot, dot, dot. Okay? And put ij, put I n comma j is equal to the interval a n comma j comma b n comma j. Okay, so basically you're looking at the product of these intervals are going to be these small squares. Okay, now for each j, these intervals, the sequence I n comma j satisfies the hypothesis of theorem 2.38, satisfies the hypothesis of theorem 2.38, of theorem 2.38. Hence there are real numbers. Hence there are real numbers. X j star in each of these intervals, 1 smaller than or equal to j, smaller than or equal to k, such that a n comma j is smaller than or equal to xj star, smaller than or equal to b n comma j for every 1 smaller than or equal to j, smaller than or equal to k, and n is equal to 1, 2, dot, dot, dot. Right? That means that setting x star is equal to x1 to xk, we see that x star belongs to in for every n, and hence it belongs to the intersection, and the intersection is non-empty. Okay, there's at least one element, and both of these allow us to prove that every K cell is compact. Theorem 2.40. Every K cell is compact. Okay, so instead of proving it separately for intervals and then for K cells, we are just killing it in one shot. We are proving it for both. Okay. Proof. Let I be such a K cell. Let I be a K cell. Be a K cell. Consisting of points given consisting of points consisting of points x is equal to x1 to xk, where ai is smaller than or equal to xi smaller than or equal to bi for every one smaller than or equal to I smaller than or equal to k. 1 smaller than or equal to I smaller than or equal to k. Okay. Then what we do is we denote what the distance or what is the size of this ball, this K cell. Put delta is equal to summation 1 to k bj minus 8 I is equal to 1 to k, I is equal to 1 to k, bi minus ai squared, all of which to the 1/2. Right? This is the standard Euclidean distance. What does that mean? Then, since this is a maximum distance of each interval, we see that anything inside the square that we are going to have is going to satisfy smaller than or equal to delta if x comma y belong to I. Okay, now of course the other way is not true. I can take 2 points far away and they might satisfy this condition, but they might not belong to I. Okay, now suppose this cell was not compact. Okay, so suppose there is a open cover which does not have a finite subcover. Suppose G alpha cover I and it does not have a finite subcover, does not have a finite subcover. Okay, well, put Cj or put Ci is equal to AI plus Bi over 2. Okay, then the intervals AI Ci and Ci Bi break this big cell down into 2 to the k small cells. Determine 2 to the k cells Qi whose union is I. Whose union is I. Okay. Well, what is happening? I have these 2 to the k cells Qi. If all of them can be covered by a finite number of G alphas, then that means I can take all of these finite number of Q alphas, put them together, and that covers the entire I. Right? So at least one of these QIs is not covered by a finite collection of G alpha. At least one of Qi cannot be covered by a finite subcollection or subcover of G alpha. Okay. Suppose for convenience, call it Q1. Call it I1. Okay. For sake of convenience, I'm going to call it I1. Repeat the entire process for I1. Repeat process for I1. Okay. And continue. And continue doing so. Okay. What that does is it gives me a sequence IN which follows the properties. We obtain a sequence IN which satisfies first I contains I1 contains I2 contains and so forth, so on and so forth. Second, each IN is not covered by any finite subcollection of G alpha. IN is not covered by any finite subcollection of G alpha for every n. And third, this is very slightly possibly harder to believe. If x belongs to IN and y belongs to IN, then the size of x minus y is at most 2 to the minus n delta. Why is this true? In each step, the size of the interval gets halved. Okay? Each interval, whenever you take AI, CI, you are reducing the size by half, right? And so the total size, if you do it n times, gets divided by 2 to the n. Okay? In fact, it can be lower, but it's at most 2 to the minus n delta. Okay? Then, by the previous theorem, therefore, by theorem 2.39, there is some point which lies in every IN. There exists x star belonging to IN, x star such that x star belongs to IN for every n, right? Well, that is one point. Since it's exactly one point, then there exists alpha such that G alpha contains x star. So x star belongs to G alpha for this alpha, right? Since alpha is open, since G alpha is open, there exists some r greater than 0 such that there is a ball of radius r centered at x star contained in alpha. B r of x star is contained is contained in G alpha, right? This implies in particular that y minus x star is smaller than r for implies y belongs to G alpha for every y, right? In your big space. Well, take n greater than 0 such that 2 to the minus n delta is strictly smaller than r. Okay? Well, then what is happening? Then C, or in my case 3, implies in belongs to G alpha, contradicting B or 2, right? Hence such a cover does not exist. Hence such a G alpha does not exist. Okay? And therefore I is compact as required. Okay? Great. We have shown that every K cell is compact. Okay? And now we will show what is known as the Hein-Borel theorem. We are actually showing something stronger than Hein-Borel theorem. Let me rephrase that. We are showing something that is a special case of Hein-Borel theorem. So it's not actually stronger, but it conveys the same information for Rn. Okay? Hein-Borel theorem says the same for any given metric space. Okay? Not just Rn. If a set set E belonging to Rk has one of the following properties as okay, let me just say this way. Let E be a subset of Rk. Then the following are equivalent. Then the following are equivalent. This is very standard notation, TFAE, which is why I'm writing it this way, so that you get introduced to it. First, E is closed and bounded. Closed and bounded. Second, E is compact. And third, every infinite subset of E has a limit point in E. Every infinite subset of E has a limit point in E. I think we showed B implies C before in theorem 2.37, and this definition is called limit point compact. Limit point compact. Okay. The fact that a limit point compact and normal compact are equivalent is a major theorem. Okay. Um, this is a very important statement which holds true for any metric space. Okay. We are going to show it here. We have already shown one way. So let's prove it. If A holds, then E belongs to I for some K cell, okay, and B follows from theorem 2.40 and theorem 2.35, which says a subset of a compact set is compact. A closed subset of a compact set is compact. Okay, we have shown B implies C by theorem 2.37. Okay, so if we show that, therefore remains to show that C implies A. Okay, so we want to show that every infinite subset of E, if it has a limit point, then E is actually closed and E is actually bounded. Okay, showing bounded is relatively easy. If E is not bounded, then E contains some points, then E contains points xn with norm of xn greater than n is equal to 1, 2, 3, dot dot dot. Right? Because if there is some n where it stops, then that would be bounded, right? The entire set would be bounded by these points. Well, the set S consisting of these points xn, xn is infinite, right? Since n is equal to 1, 2, 3, 4, and so on, you can keep taking points. If there is a biggest point, it clearly has some n, right? If there is one biggest point, look at its size. It has to be some size. Take n bigger than that. That's a contradiction, right? And clearly, it has no a limit point in Rk. And clearly, it has no limit point in Rk. If it had a limit point, the limit point is going to be finite, so it has a certain norm or bound, absolute value. And that would contradict the limit point, because limit point means for every n after a certain n, you should have them within epsilon distance. You can always take n plus 1 and it will be, or n plus 2, it would be at least one distance away. Okay? These points have no limit point in Rk and therefore in E, and hence in E. Okay? which contradicts the fact that E has every finite subset of E has a limit point, and therefore E is bounded. This would contradict. This would contradict. See? Hence, E is bounded. Great. We have shown that E is bounded. We'll show that E is closed by a method similar to how we showed it before. Suppose E is not closed. If E is not closed, then there is a point which is a limit point. There is a point in x naught. There exists x naught belonging to Rk, such that x naught is the limit point of E, but it is not a point of E, such that x naught limit point of E, but x naught does not belong to E. Right? Now, if x naught does not belong to E, then I can find a sequence of points which converge to x naught, right? With x naught not in E. For n is equal to 1, 2, 3, ... there exists xn belonging to E such that xn minus x naught is smaller than 1 over n, right? Let S be the set of such x naught, be the set of x, be the set of these xn, the set of these xn. Since I'm choosing these xn in E, S is a subset of E, then S is a subset of E, and S is infinite. And S is infinite. Okay. Otherwise, there are only finitely many points, and find the one closest to x naught. Look at the distance, take 1 over n, which is smaller than that. There's no point in there. Well, here's the thing. The limit point of S is x naught. The limit point of S, the limit point of S is x naught, and there has no other limit points in Rk. And S has no other limit points in Rk. Why is this true? Well, if there was another limit point y, okay, which is not equal to x naught, for example, if y is not equal to x naught, if y belongs to Rk and y is not equal to x naught, then they have positive distance, then distance of y minus x naught is greater than or equal to the distance of x naught minus y minus, okay, let me just say this, is greater than 0. And the distance of xn minus y is greater than or equal to x naught minus y minus the distance of xn minus x naught by triangle inequality. Okay, which is greater than or equal to, well, this distance is fixed, minus 1 over n, which is greater than or equal to 1/2 distance of x naught minus y, for at least half, for all but finitely many n. For all but finitely many, but finitely many n. Okay, so that means that y is not close to all but finitely many xn, and so it is not a limit point of E. Hence, y is not a limit point of okay, and therefore this means that x naught is the only limit point. Okay, and that means, what was I trying to show? Right. Therefore, that S does not have therefore S does not have a limit point in E. Does not have a limit point in E. Contradicting C. Contradicting C. Okay. And hence, since we are assuming C, E is closed. Closed. And that is sufficient because we have already shown bounded. We just showed closed. Therefore, E is both closed and bounded. Okay. Now, A implies B is true only for metric spaces. Okay. In general, this is not true. B implies C is always true. Actually, yeah, I think so. Yeah. Yeah, I think, yeah. But in Rn, which is what we are primarily going to be dealing with, all of these are equal and we don't have to worry. For all practical purposes, compact is going to be closed and bounded for us. Okay, so all the nice properties of compactness are going to be usable to for us for any closed and bounded set. Last theorem, theorem 2.42. This is called the Weierstrass theorem. W-E-I-E-R-S-T-R-A Strass. Every bounded infinite subset of Rk has a limit point in Rk. Every bounded infinite subset of Rk has a limit point in Rk. How do we show this? The proof is really easy once we have all the machinery set up, which we now do. Proof. Well, if B is bounded, then it is part of some closed subset, right? Being bounded, as E is bounded, as Okay, I didn't call subset E of RK. Subset E of RK. As E is bounded, E is bounded. E belongs to IK. Sorry, I for some K cell I of RK. Okay. I is compact, so E has a limit point in I. I is compact, so E has a limit point in I, and well, limit point in I implies limit point exists in RK, and hence we are done. And hence in RK. RK. Great. Easy peasy. Okay. Um, let us end this chapter with the with some properties of connected sets, or defining what connected is and showing example. Okay. Connected sets. You have some mental idea of what connected is, right? You can say that two sets are connected if you can more or less draw a complete straight line going from one point to the other, or some other thing, right? You have some idea of what connected is. However, we are trying to define it properly mathematically, and the mathematical definition is going to be slightly stringent. Two sets A and B of a metric space are called connected. So initially we are defining separated if both A closure intersection B and A intersection B closure are empty. Okay. So this means that no limit point of A should lie in B, and no limit point of B should lie in A. Sorry, slightly better. No limit point of A or a point of A should lie in B, and no limit point of B or a point of B should lie in A. Okay, so that's separated, and two sets are called connected, a set is called connected. A set E belonging to X is connected if it cannot be written as a union of two non-empty separated sets. If E is not the union of two non-empty separated sets. Okay. Proof. Not proof. Sorry. Example. Disjoint separated sets are always disjoint, but that does not mean disjoint sets are always separated. So, for example, 0, 1 and uh, 1 comma 2 are not separated, not separated. Okay. However, the sets 0 comma 1 and 1 comma 2 are in fact separated, are separated. Okay. We will show now that any interval is actually connected. I don't want to say, oh, an interval is an example of a connected set, because we have to prove that it is connected. So, theorem, which is 2.47 in the book. Okay, I've skipped some things. A subset E of the real line R1 is connected if and only if it has the following property. If and only if it has the following property. If x comma y belong to E and x smaller than z smaller than y, then z belongs to E. Proof? Okay, so in this case, what we are saying is it has to be some sort of an interval, either closed or open or half open, half closed. Any of these is fine. As long as it is some sort of an interval, it is fine. It's also saying something slightly stronger. It is saying these are the only connected subsets of of R. Okay, so let's say, suppose there exists, suppose there exists x, y, z, x, y belonging to E and z not belonging to E, such that x smaller than z smaller than or equal to y. Okay, if such a thing exists, then E is equal to AZ union BZ, where AZ is equal to E intersection negative infinity to Z, and BZ is equal to E intersection Z to positive infinity. Okay, both of these are non-empty, as x belongs to AZ, y belongs to BZ, and it is clear that they are separated and are clearly separated. The closure of BZ is at most going to be z, the closed interval z to infinity that does not intersect with AZ. The closure of AZ is going to be is going to be a subset of negative infinity to closed Z that does not intersect with BZ. So as BZ bar is contained in closed interval z to infinity, and AZ bar is contained in negative infinity to closed z. Okay, and therefore E is not connected. connected. Okay. So that is, it is connected if and only if it has the following property. So we showed that if it does not have the property, then it is not connected. Okay. Now we want to show that if it is connected, I'm sorry, we showed that if it is connected, it has the property by showing the contrapositive. If it does not have the property, it's not connected. Now we want to show the other way around. If it does have the property, we want to show that. Which way are we doing this? So now suppose right. So yes, this is the correct way. Suppose E is not connected. E is not connected. Okay. Then there are two non-empty sets AB such that A union B is equal to E. Then there exists A comma B such that AB separated, A comma B non-empty separated, empty and separated, separated with A union B is equal to E. Okay. Then do this. Pick X belonging to A and Y belonging to B. Without a loss of generality, we assume that X smaller than B, X smaller than Y, and without loss of generality, assume X smaller than Y. Okay. Otherwise, just flip the entire world around. Call B as A as B. Take some representatives. Okay. Doesn't matter. Then define Z as the supremum of A intersection X comma Y. Okay. Well, now, because it is a intersection of a closed set by theorem 2.28, Z belongs to A bar, and hence, as these sets are separated, Z does not belong to B. Therefore, so sorry, theorem 2.28 says that every closed set has all its limit points. Right, and more or less effectively it says that. And Z belongs to A bar. And therefore, in particular, X smaller than or equal to Z smaller than Y. So it's saying that since Z is in A bar, it could be potentially X, but it is also between X and Y. Is still between X and Y. Okay. The supremum could be X. Now, if Z does not belong to A bar, if Z does not belong to A, it follows that X is smaller than Z smaller than Y, right? Because X is in A, and hence Z does not belong to E, right? Because we have assumed that it is the supremum of A intersection X comma Y. If it was in E, then it should have belonged to A. If it does belong indeed to A, if Z belongs indeed to A, if Z does indeed belong to A, then Z does not belong to B bar, right? Because these sets are separated. Hence, there exists a Z1 such that Z smaller than Z1 smaller than Y, and Z1 is not in B. Then X is smaller than Z1 is smaller than Y, and Z1 is not in E as required. Okay? And so we have found points in either case which lie between X and Y which do not belong to E. Okay? Why did I write Z belongs to E? Z does not belong to E. That is why it should be. Right. And Z does not belong to E. Okay? And it's done. Okay, I'm going to stop this one here. Next time we'll start on chapter 3. Yes, chapter 3. Okay. Let me know if you have any questions.